This is how-to tutorial number 4 for Chem 1011. In this tutorial we're going to talk about the quantum numbers that we use to describe the states of the electrons in any given electronic configuration. There's N, the principal quantum number, there's L, the angular momentum quantum number, ML, the magnetic quantum number, and MS, which is the spin quantum number. So these quantum numbers ultimately represent the unique solutions to the Schrödinger equation. Okay, so when I say solutions, it's much the same as, for example, solving a quadratic equation. Okay, where you have, for example, x minus 3 times x minus 2 equals 0, and you have to solve for x. These quantum numbers here are solutions to a function, to an equation, the Schrödinger equation. And the Schrödinger equation can be used to describe atoms. And so we have the principal quantum number, which has the symbol n. Now this can be an integer, 1 or higher. So 1, 2, 3, 4, 5. We typically don't see n values higher than 5. And this pretty much corresponds to the property of orbital energy or orbital size. The angular momentum quantum number, designated by the symbol L, is also of an integer form, and it can vary anywhere from 0 up to n minus 1. In other words, the values that L can take depends on what value n is. The angular momentum quantum number corresponds to the property of orbital shape. Okay, so when L equals 0, it corresponds to a spherical shape. When L equals 1, it corresponds to what we call a dumbbell shape. And we'll talk about that in one of the later tutorials. The magnetic quantum number, designated by M with a subscript L, can take on, again, integer values, anywhere from negative L through to 0 through to positive L. And this corresponds to the orbital orientation. And so you can think of these orbitals being on some sort of XYZ axis or an ABC axis. Doesn't matter really what your three axes are called, but we need to think of these orbitals in three-dimensional space. Again, we'll talk about that in one of the later tutorials. Let's have a look at how the values for L and ML can vary depending on what the value for N, the principal quantum number, is. So if N has a value of 1, L can only equal 0. And the magnetic quantum number ML, again, can also only equal 0. If the principal quantum number is 2, then L can take on the values of either 0 or 1. And depending on what L is, ML can take on the value of 0, minus 1, or plus 1. If the principal quantum number is 3, then L can take on values of 0, 1, or 2. In this case, ML can vary anywhere from minus 2 up to positive 2. A few comments about angular momentum quantum number L. Historically, we've used a series of letters to label the L value. So when L equals 0, we label the orbital as an S orbital. When L equals 1, we label it as a p orbital. L equals 2, we label it as a d orbital. And when L equals 3, we label this as an f orbital. For example, when n equals 2 and L equals 1, we call this a 2p orbital. So we're still using the number 2 to describe the principal quantum number, but the angular momentum quantum number is designated by the letter P, and we talk about a 2p orbital. And so here's a question about quantum numbers. Determining quantum numbers for an energy level. What values of the angular momentum L and magnetic ML quantum numbers are allowed for a principal quantum number n of 3? Let's draw this. If n equals 3, quantum number L can take on values of 0, 1, or 2. In this case here, L equals 0. So ML can also only equal 0. In this case here, ML can equal -1, 0, or +1. In this case here, we see that ML can take on values anywhere from -2 to -1, 0, +1, +2. If you count these up, in total, you find that there are 9 altogether. 9, of course, is 3 squared. Notice that 3 is the number that we started with. So to answer the question, how many orbitals are allowed for n equals 3, the total number of orbitals is going to be 3 squared. To finish off, we'll talk about the fourth quantum number. This is the spin quantum number, and it has the symbol m subscript s. The Stern-Gerlach experiment described a source of hydrogen atoms being passed through a magnet. And as you can see from the figure, there was a north and south pole to this magnet, and so the beam was passing through a magnetic field. Hydrogen atoms have 1 electron in them. As you can see from the figure, what was observed was that as the beam of hydrogen atoms passed through the magnetic field, they actually split into 2 separate beams. One split upwards, one split downwards. As it turned out, this was a result of electrons being in one of 2 states. It can have this additional quantum number where ms can equal -1/2 or +1/2. This is the only quantum number that takes on non-integer values.